right, so then the next speaker is Jesús Huertas from IFT in Madrid, and he's talking about aspects of dynamical cobordism in AdS CFT. So please, Jesús, go ahead.
Okay, good afternoon, good morning. I will talk about this paper, aspect of dynamical cobordism in AdS CFT, that is based in this article that I published with my supervisor, Angel Uranga, last year. And first of all, thanks the organizer for giving me the opportunity to talk. And please, if you have any question, don't hesitate. And also, sorry if I miss someone in the citations along the talk. So let's begin with an introduction of what do we want to do. And in first place, let's talk about the cobordism conjecture. That this conjecture, this Swampland conjecture, states that, roughly speaking, every quantum gravity theory can be redeformed to another quantum gravity theory. The cobordism classes are trivial quantum gravity. And in particular, this means that every manifold, every consistent quantum gravity can be deformed to nothing. A cobordism must exist between any quantum gravity and nothing at the end of space-time. Okay. And in this talk, I will want to study the cobordism that interpolates between AdS5 × S5. That is the best study, the most studied vacuum in string theory, to nothing. The first idea that we can think of is having a bubble of nothing in AdS5 × S5. For example, the ones that were discovered by these people. But this bubble of nothing will break all the Witten bubble of nothing. This bubble of nothing will break all the supersymmetry, and by the anti-de Sitter and non-supersymmetric anti-de Sitter conjecture that state that non-SUSY AdS are in the Swampland, they don't have a holographic dual. This bubble of nothing are not what we are seeking for. So we want a supersymmetry preserving cobordism in order to have an holographic dual of this cobordism and have control on the solution. And this is what our approach will be. So we can think, how do we make a cobordism of AdS5 × S5? We can take our AdS5 and write it on a de Sitter slice. And we can say, we can put like some smear D3 branes on this S3 and that eat all the flags and our space-time will. But this is not what we will do in today. We will try to look AdS5 in an AdS4 slicing, not a Minkowski one, not a de Sitter one, but an AdS slicing of a higher dimensional anti-de Sitter spacetime. And this slicing has this metric. We have the radius R and this AdS4 part with this warp factor, where L is the 5-dimensional curvature. Okay, we can have the slicing, and now we can see the cobordism defect, the end of the world brane that is located at the nothing, at the point where we have in this side AdS5 and in this side we have nothing. But the space-time ends on an AdS4 end of the world brane. So this is the heuristic picture. What is the string theory interpretation of this cobordism? We have that AdS CFT, a stack of D3 branes, is dual to is equivalent to an anti-de Sitter space-time. So the end of the world of the brane, of AdS5 would be, for example, that the D3 branes that are AdS5 in this is equivalent to AdS5 ends on some 5 branes, D5 and NS5, and these branes are the stringy equivalent, the stringy realization of this end of the world brane in AdS4 slicing. And several related ideas with this approach. First of all, dynamical cobordism. what is the difference between dynamical cobordism and cobordism? That dynamical means that the cobordism is an space-time solution. We have the cobordism between AdS5, crosses 5, and nothing in space-time with a metric. And for this, we need a codimension 1 solution, as was explained in those articles. We have this codimension 1 solution. No? We have the radius and the non-the-world brane. So one thing that we can measure. Well, this dynamical cobordism also using this metric and this action with a Einstein frame action, canonically normalized scalar fields with potentials. They predict that the scalar fields behaves as this function near the end of the world brane with this scaling relation. This is the space-time distance. This is the Ricci curvature. Perfect. Another idea, Karch-Randall branes. Karch-Randall saw in the beginning of the millennium that if we have AdS5 spacetime, we can have an AdS4 brane, a Karch-Randall brane, and in this brane they saw that you can localize gravity. So you can live in a 4-dimensional spacetime with localized gravity, but your real theory is a non-compact AdS5 spacetime. So we will study how this Karch-Randall branes appears in this setup. Another idea is one of double holography. Double holography state, okay, we have this gravity solution where spacetime ends, and by holography, this is dual to a cage theory that lives in 1 dimension less. The plus 1 dimensional conformal field theory ends on a d-dimensional boundary conformal field theory. And double holography is the statement of, okay, we can glue together the gauge theory part that is dual to this d plus 2 gravity theory to the gravity theory that has d plus 1 dimension. So we have d plus 1 dimensional gauge theory coupled to a d plus 1 gravitational theory. And this is called double holography. And last but not least, this is also related, this approach to cobordism of AdS5 to islands and page curves in string theory. I took this picture from this article in which the author construct these islands that solve the information paradox. They reconstruct the page curve. This is, for example, the article that introduced them. And you have here a non-gravitational path. These are this radiation region coupled to a gravitational path where you have a black hole. You see, this is the same that we have here. Non-gravitational path coupled to the same dimension but gravitational paths. Okay, and this is the introduction of the talk. Let us talk about the solution. We have been talking about this cylinder of AdS5 that ends on a AdS4, but what is the concrete string theory solution, the concrete string theory realization of these ideas? We will use these pipe solutions that were studied by these people, were proposed by these people, and that consist more or less in a bag, a 6-dimensional bag, compact bag that has some AdS5 plus S5 spikes and interpolate between them. They were studying the solution of type 2B string theory with these symmetries. These symmetries are the one that preserves supersymmetry in the conformal boundary when the conformal boundary has defects. That this is what we are looking for. These symmetries translate in spacetime to a manifold that has these elements, an AdS4 that we wanted, two spheres, and an oriented Riemann surface sigma. The ansatz, the metric ansatz for this solution is this one, the AdS4 part, the two spheres part, and the sigma part. And if we decompose sigma at these two coordinates, we have that the work factors depends only on r and phi. So we will have that that in this Riemann surface, this sigma that we have here our solution change, and at some point of sigma, you have these AdS5 crosses 5 spikes, and another point you have other type of singularities. But we will be interested in the solution where we have only one throw. For example, we can choose the metric to close the bag and only have one pipe. That this will be this side. This was studied by these people, and along this AdS5 throat that ends on a bag, we have these spikes that correspond to the position of the 5 branes. As I told you before, the D3 branes ends on some NS5 and D5 branes. These solutions are completely backreacted, and you have computational control about what happens. And you can take some limits in which the solution is weakly coupled, and you can trust what is happening in the back. So we have what we want: a throat and an end of the wall brane. Yes. Okay. More intuition about the metric and the branes and the relations. The D3 branes are in the dimension 4, 1, 2, 3, 4 dimensions. The D5 in this dimension 1, 0, 1, 2, 4, 5, 6, and the NS5 branes in these other dimensions. From 4, 5, 6, we get one sphere, and from here we get another S2 sphere. From 3, we get the coordinate R, that are the coordinate and which the branes are located. And we get the AdS4 taking one dimension of this transverse space and combining it with 0, 1, and 2. And the other dimension that we have is the coordinate phi, and we get this metric. Okay. Now this is the Riemann surface sigma. In this Riemann surface, we have at each point AdS4 crosses 1, crosses 2, and we have here represented R and phi. These points are the NS5 branes and the D5 branes that are perpendicular. They are not in the same position in the field phi, and located in this axis. If you measure the flux, the free-form flux around this point, you get the flux of NS5 or D5. And also, if you measure the flux at infinity, you get the one of the number of D3s. And if you measure the flux near 0, the 5-form flux, this flux is 0, because the NS5 branes and the D5 branes eat the flux of the D3s and allows the 5 sphere to shrink at the origin, thus having the cobordism to nothing. The space-time ends at this point. Okay, asymptotically, where R goes to infinity is the AdS5 crosses 5 throat. We recover AdS5 crosses 5. Near 0, we get AdS4 times R6. This is a smooth end of the wall brane. And near the point, we get the 5 branes worldvolume. Okay. What are the parameters? What are the parameters in the theory? The parameters are, well, I plot this graph. This is also sigma. We have this case and else that are the position of the 5 branes, case from the NS5 and L from the D5. And we have also the betas and alphas that satisfy this ordering. And these alphas and beta encode the number of branes in each stack. For example, in the first stack, we have 5 NS5, and the other we have 10. It depends on the values of beta. And to finish the part of the solution, some equations. The solution, the metric that we have, this metric, is given in terms of this harmonic function H1 and H2, where these depends on the parameters in our theory, case, the position, and betas and alphas, the number, and the number of branes are equal to these things. And the metric and dilaton are given by these expressions here, where we have that double B and N are given by this function of the harmonic functions of before, and we can construct the work factor for the metric. In general, this will be very analytically very complicated, but for some cases in the article we managed to write an analytical expression for these work factors. But we will mostly in this talk we will present like the final numerical result. Okay, so let's move to our results. As I told you, we want to interpret this end of the world brane for AdS5 S5 as this stringy solution. But this is a complicated solution, as you can see, with a lot of parameters and a lot of subtleties. First of all, the 5-branes breaks the SO6 rotational invariance of the S5, which makes the solution complicated. So we need to smooth the solution first to compare with the dynamical cobordism result. If you remember, in the dynamical cobordism, we have a codimension 1. We need a codimension 1 solution. So the SO6 symmetry is broken down to SO3 times SO3. And what we will do is decompose this SO3 times SO3 into spherical harmonics. We have the SO5, the S5, the 5 sphere, that deforms due to the presence of the 5 branes, NS5 and D5s, into these SO3 times SO3 modes. So we decompose into spherical harmonics that are given by this 5. And we will keep the zero mode, G0. That is the one that is measured at low energy in asymptotic AdS, and which parameterizes the overall volume of the 5 sphere. The size of the S sphere will be given by this 0. So we will truncate our solution to this 0 mode. In detail, the first step is to compactify the two spheres. We have our general metric, as I presented before. We will reduce the two spheres, parameterizing their volumes, each volume by radians, and writing our metric in this way. This 6-dimensional metric encodes the physics of the AdS force and the Riemann surface. And the radians are given by these functions of the work factor with this coefficient. So we get a 6-dimensional theory, this one with this metric, plus the radians, the scalar fields that parameterize the volume of the two spheres. But we do not have yet a codimension 1 manifold. We have a codimension 2 manifold, and we want to have a codimension 1 manifold. So now we truncate to the 0 mode of the Kaluza-Klein-Tau. So we have that our modes, our spherical harmonics is given by this decomposition. The 0 mode function is this one. This is chosen to have asymptotic AdS5, and we extract the graviton 0 mode using this integral. It's like a inverse Fourier transform. So we finally get the 5-dimensional manifold with the truncated, the 0 mode gravitons. Next, we reparameterize the R to have an X coordinate in order to compare with the Karch-Randall results. Okay, one simple example, the genus 1 case, in which we have one NS5, in which we will apply what we have learned. This is a simple solution given by these harmonic functions, only two coefficients, K and beta, and this is a complete barriastic solution. The number of D3s, asymptotic D3s, is beta minus K squared, and the number of NS5 is given by this number. So if we specify the number of D3s and the number of NS5, we have no more freedom in the theory. And this is the result. This is the metric that we have written in a Karch-Randall form, and this is the coefficient the parameter A, we see that this goes to 0, the exponent at Rx equals 0, signaling the presence of an end of the world brane. Okay, and it's too simple because it doesn't have a bump, as we will see later. So, what is the field content of this theory? The genus 1 theory. We have the dilaton that is constant at infinity, where we have AdS5 cross S5, and that is constant at 0, where the S5 goes to 0. And we also have the radians in another parameterization, the radius of the two spheres. This one is the red one is the one that parameterizes the volume of the 5 sphere. It's constant at infinity, AdS5 cross S5, and go to 0 near xr equals 0. And this one is the purple, is the one that parameterizes how the S5 is deformed, where we go to 0. So, the dynamical cobordism interpretation. The fields go to infinity near r equals 0. We can see it here. Well, they go to 0, but this is an infinite distant point. The dilaton is constant. It doesn't go to infinity. And we can write the 10-dimensional solution as this near r equals 0. The space-time distance from the singularity is given by this r to the 8/3. The curvature and field distance scales at this number. I don't have much time, but I will be quicker. And from this relation, we get that indeed this solution, this cobordism of AdS5 cross S5, satisfy the dynamical cobordism relations with the critical exponent delta given by this number. So check, our solution satisfies the dynamical cobordism. What about Karch-Randall? In Karch-Randall, they show that using the metric, they have this profile with this cusp near AdS4. And they say that the graviton is bound on the brane, and they get a 4-dimensional massive graviton that couples to the 5-dimensional massless one. But they need this cusp to localize the graviton and to have it massive. What we have, for example, this, as I told you that it's too simple. It doesn't have the pump that is required to have a Karch-Randall localized gravity. But this is because this is the genus 1 case. We only have one NS5. It turns out that to have a bump, this bump, we need NS5 and D5-branes, both type of branes. If we introduce these branes, we get these bumps. This is A, this is X, the same as Karch-Randall. And this is an explicit realization of Karch-Randall brane in string theory. In fact, an end-of-the-world Karch-Randall brane. And we don't have the cusp, but a bump, because this is a back-reacted solution in string theory. And yes, well, this is nomenclature. This is called the bag, and this is the asymptotic AdS5. Asymptotically, we recover AdS5. And this is the end-of-the-world brane. And to end the talk, I will talk about a double scaling limit that we discovered. And this double scaling limit consists in sending alpha g+1 and beta1 to infinity. These numbers are this one, this, and this are the greatest parameter, and we send them to infinity. So the harmonic function, the first part disappears, and we get only the logarithmic part in the harmonic functions. And this implies that we get a compact red geometry. Our Riemann surface sigma is no more infinite, but is compact. We get a compact space in the form of AdS4 times x6. It is only possible if you have only both D5 and NS5. If we have this is the Karch-Randall result. If we do the double scaling limit, we get these profiles. And you can see that they are the same, but without the AdS5 throat. You keep the bag. The double scaling limit isolates the dynamics of the end of the world brane. You get the dynamics of the end of the world brane without the AdS5 asymptotic AdS5 part. This dynamic is that of a brane web. You have the D3s ending on a brane web of NS5 and D5. You get this web. And in fact provides the gravity dual of the three-dimensional boundary conformal field theory. Do you remember that you have the D3s that are dual to four-dimensional n equal 4 superjump mills, and that ends on a defect, a three-dimensional boundary conformal field theory defect that is dual to this solution that we have get using the double scale limit. It's like the dual of the AdS4. And this was also the solution alone without the double scaling limit was presented in this paper, for example. And also, ending to the double scale limit things, the fact that we can close the throat in a continuous fashion, doing this limit continuously, is related to continuously making the 4D graviton massless. As it is said in this article, the mass of the graviton is proportional to the size of the throat, to the size of the coupling between the path and the anti-de Sitter throat. And I have here a couple of slides about orbifolds, but I will pass them. I will only say that this solution can be also applied for n equal 2 orbifolds of the theory, and also n equal 3 S-folds. The end of the cobordism of AdS5 cross S5 can be extended to cobordisms to AdS5 cross S5 mod set K and S-fold of AdS5 cross S5 mod set 4. So concluding, we have unveiled the cobordism defect of AdS5 cross S5 and also from some orbifolds. We have discovered a new and interesting double scaling limit in our theory, where we recover the properties of the end of the world brane. And future direction is, for example, to extend analysis to other setups like those one, and understand the world volume degrees of freedom of the end of the world brane and its holographic dual. That this can be doing using, for example, the double scaling limit, but it is also interesting how the boundary relates to the bulk, how they talk to each other, and what constraints do they impose in each other. So I finish here my talk. Thank you very much. And yes, any question?
Okay, thank you very much, Jesús, for the very nice talk. So now we have time for questions. So if anyone has a question, raise your hand or just unmute yourselves. Okay, yeah, Arthur, please go ahead.
So this was a very nice talk. Thank you. It's very interesting. I have a stupid question. Your brane, if I think about an AdS CFT, should be thought of as an IR brane, right? Infrared brane. I mean, being on the infrared side of space, or UV brane.
That's the point, that we are not talking about this. The first thing that I talk that we are not talking about the radius is not the holographic radius that is related to the energy. This is an AdS4 slicing of the theory. So R equals 0 doesn't mean the low energy regime of AdS CFT.
So I cannot take the limit when the AdS4 curvature is somehow small. I mean, we agree that if the curvature is 0, I can always think of this brane as a IR or UV brane. Or you disagree with that? So okay, maybe my question is differently. How do I view this brane? Let's assume I take AdS5 times S5 as
yes.
being global and being described by AdS CFT. Okay.
Okay. Yes.
So what is the role of your brane in that setting?
The role of my brane is that let's think in the gauge dual. The gauge dual is not an infinite n equal 4-dimensional n equal 4 superjump mill, but is a 4-dimensional n equal 4 superjump mill that ends on a defect. My brane, my underworld brane, is the gravitational dual of this boundary conformal field theory. If you, for example, take the Minkowski slicing or the Sitter slicing, the brane is an infrared object in your dual integrated theory.
So your brain extends radially, basically.
Yes.
It cuts off 4D space. That's what you're saying.
Exactly. Yes. Goes to the conformal boundary. Yes.
What I don't understand is then, I mean, so the bubble of nothing.
Yes.
You kind of criticized it on the basis of SUSY, but I mean, what would be wrong? I could, of course, simply end AdS5 times S5 by having n branes, and then I remove the flux, and then the sphere collapses, right? I could do that.
Yes.
That would be, of course, an end of the world. That would be an infrared brane, I guess.
Of course.
Right?
Yes. Of
and
course.
You're simply not interested in this. I mean, there's nothing wrong with this.
The problem with this is that if you have to put a lot of D3 branes in order to eat the flux of the D3s that support the S5, in order to eat all the flux and shrink the S5. But if you put a lot of D3s, this will recreate another AdS5 throat. This is what we think that could happen.
I could spread them over. I could distribute them homogeneously over the S5. Separate. So each brane a point on the S5. Wouldn't that correspond to ending this road?
Well, there are n D3 branes and n's goes to infinity in order to have a weakly Karpel solution, but I think that this will be unstable. In fact, there was an article like 1 month ago of Jensen or some people on Canada that trying to do this so that you have some instability of your theory, like trying to do this, that the rotational invariance breaks, and this is precisely what will happen. We don't have a rotational invariance, we have the 5 branes that breaks down to SO3 times SO3.
You're saying that in that case that I'm describing, it will simply be unstable and a throat will be recreated in the end.
I think so, yes.
I see. Okay, thank you very much.
Thank you.
Okay, so is there any further questions? No? All right, if not, let's thank Jesús and, well, both speakers again